In this video, we are going to be looking at transformations of functions. And we're just going to start off each little section here with an example. And the function I'm going to use in my example here, and for the first several, is y equals x squared. That's not function notation. We could also write f of x equals x squared, but they are equivalent. Over here, we have the graph of x squared, and down here we have the t-table. This function I'm going to refer to as my parent function. And I'm going to compare that to the next two functions I have listed here. So the first one I'm going to compare it to is y equals x squared plus 1. So you can see what I have here is I have that parent function plus 1. So let's take a look at what that t-table is going to look like. Okay, so I'm going to use the same x values. Negative 2 squared is 4, and 4 plus 1 is 5. Negative 1 squared is 1, and 1 plus 1 is 2. 0 squared plus 1 will be 1. 1 squared plus 1 is again 2. And 2 squared plus 1 is 5. So let's plot those points for our new graph. Negative 2, 5. Negative 1, 2. 0, 1, 1, 2, and 2, 5. And I have to forgive my drawing skills are not the best on here, but if we connect those points as well as we can here, hopefully you can see that what we end up with is the same shape we had in our first function. It's just that every point that was on our first function is now moved up 1 unit. So that vertex that used to be at 0, 0 is now at 0, 1. So we can see that constant, that plus 1, took our whole graph and shifted it up 1 unit. So let's compare that to what happens when we take our function y equals x squared. This time we're subtracting a constant instead of adding a constant. So we make another t-table. And again, negative 2 squared is 4. 4 minus 3 is 1. Negative 1 squared is 1. Minus 3 is negative 2. 0 minus 3. 1 minus 3. And 4 minus 3. So let's plot those new points. Negative 2, 1. Negative 1, negative 2. 0, negative 3. 1, negative 2, and 2, 1. And again, connect those points, and what you're going to see, oops, let's erase that, we had a little crazy pencil situation going on there. Okay. Connect those dots as carefully as I can, and you can see again, we end up with that same parabola. Only difference is this time where the vertex of our parent function was 0, 0. This time we have shifted down 3 units, and our vertex is at 0, negative 3. So you can see subtracting that constant took our whole graph and shifted it down by 3 units. And this is not true only for x squared. This is true for any function that we would start with. Adding or subtracting a constant just moves that function up or down. And that's what we have summarized right down here at the bottom. We call these vertical shifts. It can either shift up or down. And if we have something that is the form of our function plus a constant, the graph is going to shift up by that amount. If we have our function minus a constant, our graph would shift down by that amount. So that's one type of transformation. Here's another one. We're going to start with that same parent function that we started with before, just y equals x squared. So we've got the graph in the table. And now we're going to take a look at y equals x plus 2 quantity squared. Notice before in the last examples on the vertical shifts, we had the plus outside of the squared. This time the plus 2, the plus a constant, is inside the squared, inside the function that we started with. So these are going to behave just a little bit differently than the last ones we looked at. Okay, so This time I'm not going to pick the same x values, and you'll maybe see why in a minute. I'm going to kind of work backwards. So this first point, -2, 4. If I wanted to get a y value of 4, what would x have to be in this situation? And I can just do a quick little solve here. Take the square root of both sides. When we're solving and we take the square root of both sides, don't forget we need that plus or minus in there. And then subtract 2 from both sides. So the x values are 2 minus 2. So -4 will give us a y value of x. And -2 plus 2, so 0, is also going to give us a y value of 4. Okay, so those 2 points match my first and last points on the table. And we could do the same thing, see what the x value is going to give us 1, and what x value is going to be a 0. Rather than writing out all those calculations, I'm just going to fill them in for you here. But we would do them the same way. So let's plot the points from this t-table. So our first point is -4, 4, -3, +1, -2, 0, -1, 1, and 0, 4. And we can connect those points, and maybe you can see again, hopefully not a surprise, we got that same shape of a parabola. But this time, instead of moving up or down, our vertex has moved to the left by 2. So adding a 2 actually moved our vertex to the left by 2. And let's see what happens on this next one. Okay, same idea here. This time I want to shoot for my y values to stay the same, and maybe you're kind of understanding why here. So let's plug in a 4 in for y on this next function. Take the square root of both sides, and add 1. So 1 minus 2 is -1. And then we also get 4 from 1 plus 2. So that's 3. And again, I could do that with these other points too. In place of 4, I put a 1 here and solve for x. But I'm just going to go ahead and fill these in for you rather than taking the time to solve each one of those. So there's our new t-table. And when we plot those points, -1, 4 would be about here. 0, 1, 1, 0, 2, 1, and 3, 4. And again, this is probably not a surprise anymore. We get that same parabola shape. Oops, sorry. My graphing is not getting any better. There we go, except you can see this time our vertex has shifted 1 unit to the right. Okay, so in summary, what we have going on here, we call these horizontal shifts. And that means the x values are changing, not the y values. And anytime we have something that's in the form f of x plus h, we have a plus of constant inside our function. That graph is going to shift h units to the left. If we have f of x minus h, subtracting a constant inside our function, our graph is going to shift h units to the right. Okay, so we had vertical shifts and horizontal shifts. Here's another set of functions we want to look at. Again, I'm going to start with that same parent function that I've been starting with each time. We have our graph and our t-table. So this time you can see we're not adding or subtracting anything with our function, but we have a multiplier there. We have 3 times x squared, or 3 times our original function. So let's take a look at what that's going to do for us. So -2 squared is 4, and 4 times 3 is 12. -1 squared is 1, times 3 is 3. 0 times 3, 1 times 3, and 4 times 3. And there's our new t-table. -2, 12 would be way up off the top of our graph, so we'll just skip that point. -1, +3 would be here. 0, 0 would be here. And 1, 3 would be here. And we only have 3 points here since the values of y get large so quickly. But we kind of know what's going on with this shape now just from our experience. So we want to connect those points with a nice smooth parabola. Sorry, it's a little shaky. Hopefully you get the idea. These aren't going to be as obvious just from looking as the ones that we just did. The shifts up and down and left and right are really nice and easy to see. But what happens here we can see when we look at the corresponding points. So on our first graph, the point -1, +1. So that was about right here. And what happened to that point? The y value got multiplied by 3. So it corresponds to this point on our new graph. So what you can see is it went, get my blue pen back. It went right up here. So each one of these points, what it does is it stretches upward. We call that a vertical stretch. The point that used to be here at 1, 1 stretched up to 1, 3. And this point that used to be right here at 2, 4, that's the one that stretched way up off the chart. That's now 2, 12. Okay? So this one, when we multiply, we call that a vertical stretch. That's if we multiply by a number bigger than 1. Now we're going to look at what happens if we multiply by a fraction, or a number between 0 and 1. And again, we'll have those same x values. -2 squared is 4, and 4 times 1/3 is 4/3. Or for graphing, it might be easier to think about that as 1.3. -1 squared is 1. 1 times 1/3 is 1/3. Or 0.3. 0 times 1/3 is still 0. This one is also 1/3. And 2, again, 2 squared is 4. 4 times 1/3 is 4/3. Or 1.3. Okay, so we'll plot those points. -2, 1.3. Just kind of have to estimate, would be maybe about there. -1, 1/3. Maybe about here. 0, 0. 1, 1/3. I think I put that one a little high. Let's see right there. And 2, and 1 and 1/3. Maybe about here. Okay, so then we can connect those points. And this time we get a much wider parabola. And again, we want to look and see what happened to those corresponding points. This point that used to be here at -1, 1 has now moved downward. We call that one a vertical compression. So in the vertical direction, the value got smaller, so it has been compressed. Or you can see that each y value has been multiplied by 1/3. That graph is kind of messy, but hopefully you understood as I was talking what was going on. So again, we call this situation either a vertical compression or a vertical stretch. And again, anytime it's vertical, that means we have changes to the y value. If you multiply by a constant that is greater than 1, the graph is stretched vertically by that factor. If you multiply by a constant that's between 0 and 1, so basically we'll generally see that as a fraction. If you multiply by a fraction, the graph is compressed vertically by that factor. Okay, so another start over again with that same parent function, y equals x squared. This time, again, now the multiplier is inside the parentheses. It's inside the function. So we're going to see something just a little bit different here. Okay, and again, I'm going to start with my y values and work backwards. Because what you're going to see eventually, when we summarize this at the end, is anytime we have a change inside the function, in this case inside the parentheses, that's going to be a horizontal change. So it's my x values that are going to change around. So I'll do a little solution, a little equation to solve here. When will 4x squared, 4x quantity squared equal 4? Take the square root of both sides. Divide both sides by 4. We get that x is plus or minus 1/2. So a negative 1/2 and a positive 1/2 will both give me x value or y values of 4. And again, I could solve for the rest of these, but I'm just going to go ahead. I know this one's negative 1/4. This is 0, and that's positive 1/4. So let's graph these. It gets a little tricky when we have these fractions, but we just do our best. So negative 1/2 and 4. Sorry, that was negative 1/4. Let me fix that. Negative 1/2 and 4 will be here. Negative 1/4 and 1 would be about there. 0, 0, 1/4, 1, and 1/2, 4. So you can probably see by my points here what I'm going to get, and this is going to be hard to draw, is a very skinny, narrow parabola in here. It's been squeezed. And again, to see exactly what has happened, we have to look at corresponding points. So this point that used to be at 1, 1, so on our parent function, that point was right here. And what has happened is that point has been transformed into this point, 1/4, 1. So it has squeezed inward. We call this a horizontal compression. Okay, every point has been squeezed in closer to the y-axis. Let's look at the second one. Same idea. I'm going to keep my same y values again because, spoiler, I'm going to tell you this is going to be a horizontal change. So 4 equals 1/4 x quantity squared, square root of both sides, multiply both sides by 4, so we get a negative 8 and a positive 8 will each give us 4. And again, I could solve for the rest of these, but I'm just going to fill them in. Negative 4, 0, and positive 4, so let's graph those points. X equals negative 8, that's going to be off my chart, so I'm going to skip that one. Negative 4, positive 1, 0, 0, 4, 1. And again, I know this has got to take some kind of a parabola shape, so I'll just sketch it the best you can. And what you can see here is we get a very wide open parabola. Again, look at that corresponding point. This point that started at 1, 1 is now stretched over to the point 4, 1. So this one, instead of squeezing in, the first one was a horizontal compression. This is called a horizontal stretch. Okay, so here's our little summary here. Anytime we have a multiplier inside the function, that's going to be either a horizontal, compress, or stretch. That means changes to the x value. And if that constant is greater than 1, the graph is compressed horizontally. If that constant is between 0 and 1, the graph is going to be stretched horizontally. Okay, so we did shifts up and down. We did compressions and stretches up and down. We have one more type of transformation we are going to look at. And we have a different parent function this time. I did change this one a little bit. So here is our new parent function. Now we're going to use y equals the square root of x, which I have graphed over here to the side. And I have a t-table over here to the left. So those are our values for our new function. So let's look at what happens if we throw a negative sign This negative sign is outside the function. It's outside the square root symbol. So I'm going to tell you right now that's going to be a vertical change. That means my x values will stay the same. The square root of 0 is 0. Put a negative in front of it, it's still 0. The square root of 1 is 1, but if I put a negative in front of it, it becomes negative 1. And the square root of 4 is 2, but throw a negative sign on it, and it becomes negative 2. So let's plot those three new points. We still have 0, 0, but now we have 1, negative 1. And then we have 4, negative 2. And since I know what a square root function looks like, I can connect those with a nice smooth curve. And I can see what that negative sign did is it just made a reflection of our parent function. So the negative sign reflected it. It was a vertical change, a vertical reflection, which means it reflected over the x-axis. And let's see what happens differently if that negative sign is inside the square root. And again, I'm going to kind of work backwards. I'm going to have those same y values I started with. So y is 0. What would x have to be? Square both sides. Negative sign doesn't really matter. It's going to be 0. What if y was 1? What value would I need for x? To get 1, y square both sides. Multiply both by negative 1. So x would have to be negative 1 to get a y value of 1. And again, I could do that for the 4, but it's going to end up, or sorry, for the y equals 2, it's going to end up being negative 4. So when I plot those points, 0, 0, negative 1, 1, and negative 4, 2, and plot those with a nice smooth curve, and you can see again, we get the same shape as the parent function, except this time instead of reflecting it up and down, a vertical reflection, it reflected over side to side. That's a horizontal reflection, or a reflection over the y-axis. And here's our little summary. Anytime you have a negative sign outside of your function, it's going to be a vertical reflection. Anytime you have a negative sign inside your function, it's going to be a horizontal reflection. So I do have this little summary chart. When I first started teaching this, it was even hard for me to remember all of these. And so I was thinking about a way I could sort of organize it to help me remember it. And the way I found that works best for me personally is to think about all these changes we just talked about as falling into two categories. They can either be a vertical change or a horizontal change. That vertical change means it's going to be changing the y value. Horizontal change means it's going to be changing the x value. I don't know why everything's jumping around on me here. So vertical changes are always outside of the function. Notice here's our original function plus a constant. Our original function minus a constant. A multiplier outside the function. Either the multiplier bigger than 1 or smaller than 1. The negative sign is outside the function. Anything that is outside the function is a vertical change. It's either a shift, a stretch compress, or a reflect. The other thing to remember about vertical functions is they make intuitive sense. You expect when you add a constant that it's going to shift up. When you subtract a constant, it's going to shift down. When you multiply something by a number, that's going to make it bigger. It's a vertical stretch. When you multiply something by a fraction, which is basically what's going on here, a constant between 0 and 1, when you multiply something by a fraction less than 1, it's going to compress. It's going to get smaller. Okay? Similarly, these horizontal changes are a little bit counterintuitive. So here when we're adding h, when you think about your coordinate axes, the positives are on the right and the negatives are on the left. But this sort of goes backwards to what you think. When you add h, it actually shifts to the left. If you subtract a constant, it shifts to the right. Same thing here. If you multiply by a positive whole number, a positive number bigger than, sorry, this should say greater than 1 right here. A constant greater than 1, it actually gets smaller. Usually when you think about multiplying, making things bigger. And here, when you multiply by a fraction, it actually stretches, it gets bigger. So the horizontal transformations are a bit counterintuitive, but if you put them all into that category, it will help you remember the direction they need to go. So anyway, let's look at a few problems. Here's one example. There's a lot of different kinds of transformation problems you could see. I just picked a couple here to look at in this video. So in this graph, they gave us y, or f of x equals the absolute value of x. Right here's the picture. It makes kind of like a V shape. Okay, using transformations, we want to graph this new function. So let's pick a different color. We want to graph this g of x equals negative absolute value of x plus 1 minus 2. Okay, so we have a bunch of transformations going on here at once. We're jumping right in. When you evaluate your transformations, you need to think about order of operations. So we're going to start inside the absolute value, because absolute value is like a grouping symbol. So the first thing we're going to talk about is this plus 1. I'm labeling it A. So over here I'm going to talk about these in order. Then the next thing, after inside the grouping symbols, would come multiplication, comes before addition and subtraction. So here we're multiplying by negative 1. That'll be the second transformation we talk about. And then lastly, addition and subtraction, we'll talk about that negative 2 last. So there are 3 changes happening to our original parent function. The first one is plus 1 inside the function. So if it's inside the function, that means it is a horizontal change. I always just like to think about, before I even start, which category is this transformation. This is a horizontal change, and since it's an addition or subtraction of a constant, that means it's a shift. And plus 1 always goes 1 unit to the left. Again, it's horizontal, or kind of counterintuitive to what you might be thinking they should be. The next transformation we have is that negative sign. It is outside of the absolute value, so anything that's outside of our function is a vertical change. And a negative sign is always a reflection. And since it's a vertical reflection, that's got to be a reflection over the x-axis. The last transformation that we want to look at is that minus 2 at the end. Again, since it's outside the absolute value, that means it is a vertical change. It's addition or subtraction of a constant, so that means it is a shift. And again, the vertical ones make sense. Since it's minus 2, that means our whole graph is going to go down by 2 units. And then what I like to do next is just kind of go pick a few reference points and point by point look what's happening here when we make this transformation. Okay, so on our original function we have a point right here. This is the point negative 2, 2. Okay, I'm going to apply these 3 transformations to this point to find the new point on our new transformed graph. Okay, so first step, I have to take that point and shift it 1 unit to the left. So that means instead of negative 2, 2, it's going to be negative 3, 2. And then my next step is a vertical reflection over the x-axis. So that means instead of being positive 2 for the y-coordinate, it's going to become a negative 2. That's what it would look like if it reflected over the x-axis. And then the last step is I'm going to take that point, I'm going to shift it down 2 more units. So that means instead of negative 3, negative 2, it's going to scoot down and be negative 3, negative 4. So this is going to be one of the points on our newly transformed graph. Next up, I'm going to take this point that used to be the vertex of our graph. I'm going to see what happens to that after we apply these 3 transformations. So first up, I take that and I shift it 1 unit to the left. So that means it becomes the point 1, 0. Then I'm going to reflect it. Well, it's on the x-axis, so when I reflect it over the x-axis, it doesn't actually change at all. And then I'm going to shift it down 2 units. So that means it's going to be 1, -2. There's our new vertex right there. So I picked a point on this sort of side of the graph. I picked the vertex, and then maybe pick one more point on the other side of the graph just so I can make sure I haven't made any mistakes. I'm going to use +2, +2, and transform that. Step 1, shift it 1 unit to the left. Step 2, reflect it. So it's going to jump down to 1, -2. And step 3, shift it down by 2 units. So that means it's going to become 1, -4. And because we know the shape of our original graph, those 3 points give us enough guideline to draw our new transformed graph. Okay, let's do one more of these. Here's another one. This time our parent function is the square root function, and we have it graphed over here. And our transformations that are going to take place, we've got 3 of them again, order of operations. So I'm going to start off inside the function. That's going to be first, and then multiplication, and then addition and subtraction. The order can be important, so it's important to watch out for those order of operations. And first up, I just like to list the functions. It helps me keep things straight and think about it in my head. That +4, it's inside the radical. That means it's inside our function, and anything inside the function is a horizontal change. A plus or minus is always a shift, plus or minus of a constant. So this is going to shift 4 units to the left. Remember, the horizontal transformations are a bit counterintuitive, so it doesn't go in the positive direction, it actually backs up. Next up, B, I'm going to talk about multiplying by 2, multiplying by a constant. Since that 2 is outside the radical, it's outside my function, so that means it's a vertical change. Anytime I multiply by 2, that is going to be a vertical stretch by a factor of 2. And the last one we have -1. Again, that -1 is outside the radical, so it's a vertical change, and that's going to be a shift down by 1. Okay, again, we're going to pick a few points off this original function and look at what happens to them when we put them through the transformations. So 0, 0 is sort of the ending point of our original function. So the first thing we do, step A, shift that 4 unit to the left. So that now becomes the point -4, 0. B is a vertical stretch times 2. Vertical, again, is a change to the y value. So 0 times 2 is still 0, so it doesn't change in that step. Then finally shift it down by 1 unit. So that becomes -4, -1. This is now the starting point for our new transformed function. Our original function has a point right here at 1, 1. So let's see what happens to that one. Shift it 4 units to the left, and it becomes -3, 1. A vertical stretch times 2 means we're going to take that y value and multiply it by 2. And then the shift down by 1 unit means we're going to subtract 1 off the y value. And there's our new point, -3, +1. And then maybe just one more point, make sure I'm sketching exactly what I need it to be. Oops, sometimes that pen just kind of jumps around on me. Okay, so another point on our original function is the point 4, 2. And if I take that point and apply these transformations, I shift it 4 units to the left, and that makes it 0, 2. Vertical stretch by 2, so that means take the y value and multiply it by 2. And then a vertical shift down 1 means subtract 1 off that y value, so 0, 3. And there is our new transformed square root function. So it took it over to the left, it stretched it up vertically, so every point moved up, and then it shifted the whole thing down by 1. Okay, transformations definitely take some time and some practice, but hopefully this gave you a good start.